So now we come back to this problem, and at least we need to have an idea of what is going on here. We have a plane that the actual flight path of the plane will be equal to, the plane's path will be equal to the original path of the plane. We'll call that V, plus what happens to the wind. So our original plane, let's see what's happening here. You know what, I'm going to draw two different sets of XY coordinates here. So the plane is going to be, its original attention's V plus W for wind. So let's talk about the V vector. It says that the plane is set to go 500 miles an hour at a bearing of 330 degrees. So this is our vector V. Notice its bearing is 330 degrees. They use the word bearing. So that's where it's headed, and its magnitude is 500. All right? That's our plan. Like we're in a satellite over the Earth, and we see, okay, that's the flight path of the plane. It's going to the northwest. By the way, a bearing of 330 degrees from north is the same as saying north 30 degrees west, because this angle here would be 30 degrees. All right, how about the wind? It says the wind, I'm going to draw another XY chart, and I'm going to say the wind is blowing. It said north 45 degrees east. And if this is the wind, they said the wind's magnitude was 70 miles per hour, because that's the speed. All right. So here's my situation. I've got to take the vector V, which is the intended flight's path. I love vectors. Why? Because I can click and drag them. I'm going to click this vector and I'm going to drag it and do vector addition. So there is vector W, and our resultant vector is going to be from the tail of the first to the head of the last. So I'm drawing it dotted green. This vector is P is equal to V plus W. That's what we're after. So here's my picture again. The plane is equal to the plane's intention in a windless environment plus the wind. We're adding vectors. The plane has speed and direction, or magnitude and direction, and the wind has magnitude and direction. So that's why I'm treating these as vectors. They're actually vectors. They both have magnitudes and directions. So let's make a roster. We know that the plane's original intent was V, and they tell us, well, let's write it in polar form. Cosine theta I plus sine theta j. Now we've got to figure out what's going on with V. Well, they told us that the plane is going at a speed of 500 miles per hour. So the magnitude of V is 500. Now the bearing here is 330 degrees clockwise from north. Now they just said 330 degrees. We have to understand that's clockwise from true north. If that's 330 degrees, then this little wedge of cheese here is 30 degrees. And our math angle, or our direction angle, is this one here, which of course is 90 plus 30 more. So our angle is 120 degrees. Well, I was expecting something between 90 and 180 because we're in quadrant 2. So there's the trickiest part of this problem. Converting from a bearing to a math angle or a directional angle. So V is equal to 500 cosine 120 I plus sine 120 j. That's our V. How about the wind vector? Well, we know wind was equal to the magnitude of the wind times cosine of the direction angle I plus sine of the directional angle j. So the wind was equal to, well, they gave us that the wind was blowing at 70 miles per hour. If I just look at this wind vector, note I want this angle. There is my theta for the wind vector. And they told me it was north 45 east. So that means this angle has to be counterclockwise from the positive x-axis. The one I use in my formula here has got to be 45 degrees. 70 cosine of 45 degrees I plus sine 45 degrees J. Now, look at this is important, and so is this. That's the tricky part, converting 330-degree bearing into a math angle or direction angle of 120, converting north 45 east into a 45-degree angle. And I'm finding that angle. The angle, I say it again, the angle I use in the formula is always positive theta in the formula. This theta here is always counterclockwise from positive x-axis. We call this the math angle, the directional angle. Even though they gave me bearing, I had to transform it into something that the equation could use. What's the next step? Well, it's to say that our plane vector, which we're interested in, let me do it in a different color. Let's go purple. How about that? Our plane vector is equal to our initial settings on the airplane plus the wind. So our P vector is 500 cosine 120 I plus sine 120 J plus the wind vector, which was 70 cosine 45 I plus sine 45 degrees J. Now, what's my task? I've got to distribute, 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 distribute. And then what I'm going to do is add my i's and add my j's. So this plane vector is 500 cosine 120 I plus 500 sine 120 degrees J plus 70 cosine 45 degrees I plus 70 sine 45 degrees J. Now look what I have. I have my I's here and my J's here. I'm going to add these I's up and add these J's up. So what I'm showing here is I reorganized. My I's are together. Those are my X components. And my J's are together. Those will be my vertical or Y components. And so when I do this, I'm combining the I's and I'm combining the J's. And what you'll get when you do this is negative 200.5 I plus 482.5 J. Now, remember what we had here. We had vector V and then vector W, and we said this is vector P, which was V plus W. And we just found the components of vector P. We're saying that that's negative 200.5, and this vertical side is 482.5. So don't forget what you just found. You found the resultant vector P, and these are its components. Now, if we wanted to put it in component form, of course, it would be negative 200.5, comma, 482.5. So did I have to use my calculator? No, I could have used my unit circle, but I wanted to figure out what these were and get a decimal because it makes more sense to me if I'm trying to figure out what the direction and speed of a plane are. Well, those are the components. What I want to know is the magnitude or the speed of the plane. Of course, I'm going to take my components. I'm using the Pythagorean theorem here. So important to understand what we just found. Because if you don't understand what you just found, you won't be able to do this, right? You just found, when you say P is this component, you're saying this resultant vector here, which is the plane's course plus the wind, will give us our final vector P, or our resultant vector P. And we found its components. Of course, we were expecting negative, positive based on our picture. Now, when you crunch the numbers, and of course, this would be a calculator, we get 522 it's about 522.5 miles per hour. Now, I ask you, does that make sense? If the plane is pushing this way and the wind is pushing this way, do we expect the plane to get a little boost by that? In other words, is the magnitude of this vector expected to be bigger than the magnitude of the plane's original settings? Yeah, we've got a little bit of a tailwind. How about, given that we found the components here, how do we find this angle? This will be its directional angle theta. Well, of course, tangent of this directional angle theta is equal to opposite 482.5 over adjacent negative 200.5. So theta is inverse tangent of 482.5 over negative 200.5, which gives us theta is equal to, well, look, I know that when I take inverse tangent, I can only use quadrants 1 and 4. I'm expecting an answer in quadrant 2 based on my picture. And based on my components, a negative positive puts me in quadrant 2. When I do this, I get negative 67.4 degrees. That's this angle here, negative 67.4 degrees. Holy cow, our calculator's all messed up. No, it's not. We wanted this angle, right? So remember, the period of tangent is 180 degrees. You're just finding the wrong tangent. Add 180 degrees to that, and you get 112.6 degrees is equal to theta. Now, what did we just find? Look at your picture. We found that this is 112.6 degrees. So if this is 90, then this little wedge of cheese here is 112.6 minus 90, which would be 22.6 degrees. So the problem asked us for the bearing. If you put this as the bearing, you'll be wrong. This is what we call the direction angle. And that is the angle used in the formula. We have to use that in the formula. If we were gonna write this vector in its polar form, we'd say vector P is equal to 522.5 times cosine of 1112.6 degrees I plus sine of 1112.6 degrees J. That would be polar form, and that's appropriate. 112.6 degrees is appropriate. But they asked us for the bearing. And I think the easiest way to do bearing is to say it's northwest. Clearly, we're going to the northwest, and we're bending this 22.6 degrees west. Now, you could also say that the bearing is 360 minus 22.6. So if you wanted to report this bearing all the way to there, you'd say it was a bearing of, from clockwise from north, you just write north 337.4 degrees. I kind of prefer this one because it tells me right away we're in the northwest quadrant. So what is the final answer? 522.5 miles per hour at a bearing of north 22.6 degrees west. What's the biggest problem? Students report this answer, and that's not the bearing. I want the bearing.